Hello, everyone. My name is Chris Piech, and it is my great honor to be here virtually with you today in EDM to present on measuring ability to learn using parametric learning gain functions, work by me, Engin, and Fritsch. So, as you know, traditional tests, and by tests I mean like assessments, things you see in school, they measure ability. Could be in different subjects, could be in math, could be in science, but generally tests measure your ability to do stuff. There's lots of examples of these, but you can imagine something like PISA. They do this big test around the world and measure people's abilities and things like numeracy and literacy, and then they rank countries in that ability. Lots of other tests do this. There's a company in the United States, there's NWEA, and they measure people's ability in mathematics over different parts in people's learning experience in different parts of the United States. But there's a critique of these tests. Hey, maybe for students of the future, it's not so important what they know. Perhaps what really matters is how well we've prepared them for future learning. The jobs of the future don't even exist today, so how can we teach them for those jobs? Instead, one of the things we really should be teaching our students is how to acquire new abilities. So on that note, today, I would like to talk to you about a whole new and exciting type of test, a test on ability to learn. And it's so cool. I'm incredibly jazzed about these. Tests of ability to learn could work in lots of different ways, but instead of getting something like a question which says solve this math problem, you would probably get something like tasks where you're shown a learning experience and we're going to measure how well you can acquire new abilities. So maybe you show up and we say, today we're going to teach you how to program. Then we first measure how much you already know how to program. Then we give you an authentic learning experience, and afterwards we measure how much you knew after that authentic learning experience. Your ability to learn should modulate how well you're able to go from your pre-ability to your post-ability. This could exist for lots of different subjects, not just for coding. You could do a learning task on coding. You do a learning task on language. You could do a learning task on anything you wanted. And if you gave a student lots of these different learning tasks, and if you gave lots of these different learning tasks to lots of different people in different populations, maybe you could measure not ability, but ability to learn. How exciting. It's so exciting that PISA, that company I was telling you about that does the world test, in 2024, they're going to try to, for the first time, measure ability to learn of school systems around the world. But there is a problem. When we talk about tests of ability, there's all these great things we can do. We can take lots of students working on lots of different problems, and we can turn it into a single number which represents the ability using a clean mathematical expression that we have lots of evidence for. And because we have this nice mathematical model for tests of ability, we can do things like formally reason about fairness and confounds and mixture effects. We can't do that for these new exciting tests until today. So as a little bit of background, I mentioned tests of ability are able to do all these things because they have a formal mathematical model. You probably already know this, but they have this model called item response theory. And item response theory is a mathematical model that says, hey, if a person I interacts with a problem J, what's their probability of getting it right? And because they're able to precisely model that probability, they're able to do things like take lots of evidence and backtrack the abilities of each of the students without being distracted by the difficulties of the specific problems that they solved. It's a good time. It leads to all the goodness I just showed you. Today, let's see if we can do that stuff for these new learning ability tests. But we have a first complexity. In tests of ability, you just have one number. Every time a student interacts with a problem, they either get it right or wrong. In tests of ability to learn, every time the student interacts with the learning experience, you get two numbers, what they knew before and what they knew after. And this makes it much harder to come up with a single ability. And you can't just use item response theory as it already exists. What are we to do? Well, let's look at some of these graphs. Here's two different graphs from two different populations. For every single student, they're going to be circles, and let's look at what they knew before and after. So if we take what they knew before, that's their pre-score on this learning experience, and we look at what they knew after, that's their post-score, that would make 1 point in this graph. And if we took a whole population, you can see what was their transformation, their function, from pre to post. So this is for one population, this is for another population, and you can see that this dotted line, that represents the function that is mapping pre's to posts. Cool. Not one number, though. We need to figure out some way to get these graphs into one number that says, how well was this population able to learn? How are we going to do that? Well, one traditional way that people first proposed was maybe we can look at the expected gains in learning for this population. So we can do the expectation of what people have learned, and that's their post ability minus their pre ability. And if we look at expectation of that population, this L number, that could give us a number which says, how well are these people able to learn? And that number says these people were able to learn really well, and these people were not very good. But there's a problem. What's the problem, Chris? these two populations are actually the same learning function. If you took two people from either of those populations, if they had the same pre, they would walk away with the same post. Their ability to learn is the same. The reason we got these two different numbers when we use this old school calculation is simply that the people in the blue population had different prior knowledge than the people in the red population. Same ability to learn, different prior ability, and it just led to this really big confusion. So there's two things I want you to know at this point. One, I want you to think about learning as a function from pre to post. And let's see if we can get formal about that function. And the second thing I want you to know is you have to be really careful to consider the effect of prior knowledge on posterior knowledge. And if you're not careful about it, you might be not measuring ability to learn, but just simply what do people already know. Back to tests of ability. That's not what we wanted. So these learning functions, there's mappings from pre to post, and it's a really big concept for these tests of ability to learn. And specifically, let's be thoughtful about considering prior knowledge in these learning functions. Here's one way of thinking about the learning functions. For any person coming from a population, when they interact with a particular task, those two things come together to produce a learning gain function, and it's going to come up with a function that maps people's prior abilities to their posterior abilities. Now, each person is going to come from a population. So maybe we're going to think about the learning ability of the population instead of the learning ability of a particular person. But you could use this mathematics for either measuring people's ability to learn or population ability to learn. Fun times. But basically, ability to learn and difficulty of task, they lead to a function. And that function is going to take priors and pump out posteriors. What we really want to get to is this variable itself. We don't really care about the priors and posteriors. We care about ability to learn. How could we come up with a nice mathematical representation? If we could write this in mathematics, tomorrow I can get you abilities to learn for all your students. What a good time. So key challenge, how can you write a mathematical expression that captures all that interactions? And if you can write it mathematically, then we can figure this out. As a brief aside, I got so excited about this mathematical problem that I didn't get COVID-19. I can tell you all about how I didn't get COVID-19 because I got excited if you ask me in questions later. So we had to come up with a mathematical expression. Where do you start with a question like that? Well, we started with hypothesis generation with a really intelligent simulator. We built the most complicated simulator we could of learning. We simulated all these learning theories, and you can check out all the things that we put into this simulator in the code. But basically, we came with this really complicated simulator, and we simulated a whole bunch of people going through the learning experience. And then we looked at what do these functions look like? They're these pre to post functions. And we saw a whole bunch of different functions, but we noticed a pattern. Basically, they look like either one tail or another tail of a normal distribution or a middle bump. You know, there is some learning experience where people who had low prior learn the most. There's some learning experiences where people have medium knowledge learn the most, and some learning experiences where you really had to have a high prior knowledge to learn anything at all. These look like really different graphs, but you know, we thought actually all these graphs can be described by the same mathematical function. Woohoo! Check out the paper for all the details. But this is a mathematical function that takes somebody's ability, some characteristics of the particular problem you're looking at, and leads to a function which can map prior abilities, posterior abilities. Exactly what we wanted. Yay! Are we done? No, we're not done. Because I've just given you a theory. I've given you no reason to believe this actually works. But good news, it could. Of course, we won't really know until we see like an amazing example of one of these learning tests. We couldn't find an amazing example, but we found some really good proxy things from which we could measure this cool new theory we have. First, we measured our cool new theory on simulation. You know, like, can we backtrack simulated people's ability to learn just by looking at these pre and post numbers using this new theory? Should be yes, and more importantly, we tried it on some real world data. So first on the simulations, unsurprisingly, our learning gain function theory was able to perfectly back out people's ability to learn. So even though the function couldn't see ability to learn, using the nice mathematical theory that we had, we could back out ability to learn basically perfectly in simulation. You know, it's just simulation. But more importantly, for NWA, which I told you about earlier, and this other data set that had some learning experience between people's pre and posterior, we were able to show some promising improvements over the state of the art. So the state of the art really is to come up with a linear model, and a linear model just says that people's posterior learning will be controlled by a linear line. Maybe it doesn't really fit those things we hypothesized from the simulation, but it wasn't a bad idea. Using a learning gain function, you're able to do a much, much better job of describing the data in the NWA data set. Fantastic. It did well, but not extraordinarily well on this other data set that had a learning experience. It beat the ubiquitous state of the art. It was much better than using something like polynomial. And it was basically tied for this linear multi-parameter model. The linear multi-parameter model has not one number to represent ability to learn, but several numbers to represent ability to learn. And a cool thing is, using one number to represent ability to learn in our function, we're able to match using multiple numbers. That's a bit of a win. You know, these aren't huge wins, but they're bits of wins, and they're good signs that we're on to a good direction. Then we can go back to all our data and gain some insights. You know, we went to NWEA and we looked at all the learning gain functions for people in 4th grade, 5th grade, 6th grade, 7th grade, 8th grade. You know, we made sure our simulation was able to describe this data. We looked at what top schools look like. We looked at what top schools for people who didn't have much prior knowledge look like. And we got all these cool visualizations of actual real world learning gain functions. For every single school in NWA, we were able to then calculate an ability to learn. This is different from students' ability, which NWA normally calculates. We calculated their ability to learn. And cool thing, if you look at all the schools in MWA, you see that it looks Gaussian. There are some schools which are really, really great at teaching people how to learn. And there's some schools that aren't that good at teaching people how to learn. Now, you might be wondering, is ability to learn just basically the same as ability? And the answer is no. There's not that much correlation for schools' ability and ability to learn. The R-squared is only 0.08. There's plenty of schools where students don't have that strong ability, but their ability to learn, when we've taken into account prior in a very careful way, was really high. And some schools that have really smart students, but they're not really teaching their students how to learn. A new insight into schools of America. Who knew? Good times. Now, of course, in conclusion, since we have this nice mathematical model, because it's doing a really good job on real world data, we can start to do all those cool things that you could do with traditional item response theory. We now have a mathematical model for ability to learn. What a good time. We leave this as an open challenge. This is just the start of an amazing journey. Come join us. Think about, could you come up with a better function than we came up with? Or maybe you want to do something fancy, like use a neural network. The world's your oyster. Anyways, today we talked about a whole bunch of interesting things. We introduced this challenge of modeling ability to learn. We introduced, this probabilistic IRT model for ability to learn. And we showed that it matches simulation, and importantly, we showed that it matches real world data.